the main crux of our science is that we're here to accelerate things quickly, up to very high speeds, and impact them into other things. And we study the product. And that manifests in a few different ways. And so we have a few different types of launch facilities or accelerators to get at different types of objectives, of whatever the objective of either us as an internal researcher or as an external scientist. So we have people come here from all around the country and all around the world to conduct experiments using these facilities to either shock materials or look at the effect of impacts on whatever it is that they are studying. So these impacts that we study take form at a few different scales. So when you think of impacts, you might think of impact craters, these huge basins, either on the moon, or you might think of Barringer Crater in Arizona, where you see this nice bowl-shaped depression in the Earth's surface. And while we don't have a ton of impact craters on Earth because we have plate tectonics and we're also shielded with our atmosphere from the small impacts, elsewhere in the solar system, when you have airless bodies or planets that don't have atmospheres, they're subjected to smaller and smaller impactors. And the effects of those impactors can add up over time. Also, you can think about shielding for flight hardware. So you have spacecraft that we want to protect, GPS satellites, weather satellites, people in space. And we want to make sure that we can protect our astronauts and our equipment. Sorry, I'm getting a pop-up message on my computer that it's going to restart in an hour. And now I can't see myself. Hang on one second, I apologize. So where was I? Oh, the scale of impacts. So when we're talking about large impacts, you've seen Hollywood movies where Bruce Willis will go and land on some asteroid and try and blow it up to protect Earth. But really what can be dangerous for astronauts as well is flecks of paint that are floating around low Earth orbit. These things are traveling at 17,000 miles an hour, and a fleck of paint going that fast can do quite a bit of damage. In this lab, it's not a main part of our studies, but impacts into metal. So this is a aluminum plate, and you can imagine a fleck of paint can do quite a bit of damage at high speeds. And imagine an astronaut going and holding on a handhold, and you have a small impact crater with these very sharp edges. It's not hard to imagine that can become a problem very quickly. So the flux of these impactors in space is a rather important thing for us to understand and what they can do. So the first of the three guns that I'm going to show you on the lab tour today is called the flat plate accelerator. Now I'm going to do this in a couple different ways. I'm going to show you the gun first. It's this one in the front here. And then I'm going to tell you a little bit about how it works and what it does. So the main objective of this gun is sample recovery. So what we're interested in here is taking a piece of rock, shocking it to a known pressure and temperature, approximated temperature, recovering it, and then allowing the investigator to look at that rock that's been to a known pressure, a known thermodynamic state, and they can look at the microstructure. They see defects, they see cracks, they melt, and they go, okay, when you see that type of feature, that correlates with X amount of pressure. And we could do that over a range of pressures and sort of start to correlate or come up with schemes that allow shock calibration. So when you can pick up a rock on the Earth's surface that's been subjected to shock, you can look at the microstructures and say, oh, we think that the shock pressure was around 40 GPa because we see similar microstructures as to what we saw in these types of experiments. So how this type of work happens is with this extreme amount of energy that we're dealing with this gun, we're usually shooting between 1.5 and 2 kilometers a second for the impacts. So recovering your rock is not a small feat. It's very easy to turn things into dust and vapor at those energies. So we need a fairly substantial piece of steel to hold the rock during that shock event that we can then cut away to reveal your rock. So this is the basics of our sample container. It's just a chunk of steel with a hole in the center, a well. And then inside of that, we're going to put another piece of steel and then machine this flat. Now inside of this smaller one, I'm going to set this big guy down so it'll drop on my laptop. There's two pieces, and inside of this piece, we can drill out a well that's less than 1 millimeter deep and about 1 centimeter wide. And that's the size of your sample. So you'll have a little disc, little cylindrical disc of your sample that'll go inside of here. It'll get sealed up really tight. So it's metal on metal, both sides of your sample. That will get inserted into this metal sample container and then machined flat. So you can imagine it'll just have a nice flat surface with your sample sitting somewhere about 1 centimeter back from the face. Now, how we impact this, how we shock it, is with a flyer plate. So we have here's a flyer plate. It's another thin disc of metal. This one's copper. And what we can do is embed that inside of some plastic, which we call a flyer. This is a flyer assembly. And this is your actual projectile. So this is the thing that gets accelerated down the barrel and then impacts your sample. Now, when that impact happens, you have a thermodynamic state that's reached between these two metals that's dependent on how fast this projectile is going when it impacts. And if it impacts nice and flat, we know the pressure that would be generated by those two metals impacting at that speed. And since your sample is in the middle of this metal container, it will equilibrate to that pressure. And so after this impact happens, we can machine away some of this metal, extract out your sample of rock, give it to the investigator, and they can go off and do what they will with it, look at microstructures or spectra or whatever they're interested in. So just to show you what this kind of looks like, here's our nice polished new one, and here's a sample container that's had a rough life. So this is after an impact. And it's hard to imagine at first when you start seeing these things. It's quite a bit. It's hard to see on here, but it's probably about 6 millimeters depressed from the face. And that happened with a piece of plastic and a tiny piece of metal that was 1 millimeter thick. So it's quite a bit of energy. So now let me show you how that looks in the gun. So going back to our gun, this is our breech assembly. This is the very end of the gun. This is where it all starts. So this is where we put the gunpowder into the gun right here. We will attach an electronic primer to this end that allows us to fire the gun from the outside of the lab. Whenever we fire any of these, we make sure that we're outside behind some fairly thick walls and we're safe from any blast that would to occur, something bad. That's never happened, but just in case it does. Our flyer plate sits about right here in the assembly. And so after we ignite that gunpowder, it then starts going down the barrel. The barrel is about 6 feet long, and it's accelerating from standing still to about 2 kilometers a second in that time frame. It then enters this big white chamber here in free flight. So as soon as it leaves this barrel, it's in free flight. It's flying through here, and then we have a series of lasers. And these lasers have a known distance between them. The projectile will occult those lasers in series, and since we know the distance and we know the time that it breaks all of these lasers, we have multiple measurements of how fast this is going, and that's how we determine what pressure the sample reaches. It then enters the impact chamber here. We have cameras set up on either side of the chamber and a flash, and that flash goes off right when the sample is entering the chamber, and I'll show you where that happens. So inside is a target bucket right here, and you see that cutaway in the target bucket. When the projectile is inside that window, that's when we snap our picture. And we do that to make sure we can actually look at the orientation of the sample in space right before it impacts the sample, because the physics involved in determining the pressure that's achieved relies on a perfectly planar impact. So we need that tilt of that projectile to be very little. We want it to be as straight up and down as possible. And so once the projectile hits that, the sample container goes flying into the back of the chamber, which I did not open up, but then it's eventually stopped by a backstop. And you can see this thing is pretty, it's had a rough life too. The sample containers hit that thing going pretty fast. So let me show you what that arrangement of that bucket looks like really quick. So here's that target bucket. On the inside, it just simply has two cylindrical pieces of metal that our sample container sits on. And so that projectile, here's our Top Gun fighter plane simulation. So that metal rod isn't there. This is just so I can sort of demonstrate. It flies through here. It enters that window. We take its picture. It then hits that sample container. This thing goes flying. So it's pretty simple. It's just a gun that shoots a very weird looking bullet. So I want to show you what some of these pictures look like really fast. So I'm going to pull this up. And please, someone verbally say if you can see it, because I can't see anyone. All right, perfect. So these are two different images, two different impacts. And so here you can see the projectile in flight, if you can see my cursor. The image on the left is taken at a relatively low shock pressure. And I'll get to why I know that in a second. So this thing is coming through. We're taking a very fast picture, and we use this to determine the tilt. Now, if we look on the picture on the right, I know this is a much higher shock pressure because you see how bright this is. So we have a flash that will expose this flyer, or the projectile in flight. But then once it impacts that target, it creates a very bright flash, and it will expose the cameras again. So this is the projectile as we took the flash, but then you see this cone. That's actually the back of the projectile as well. It's being exposed on the camera as it impacts the target because it's creating its own flash. So you're basically double exposing the film. So it's pretty neat. Now there are some ups and downs of using this type of gun or accelerator. The one positive here is that we get to recover our sample. That's very important when you're trying to look at microstructures as a function of shock. But there are some thermodynamic consequences to that. So if we're looking at shock pressure as a function of time, the method that we're using is called shock reverberation. We have to bounce this shock wave off of that metal container multiple times to reach the target pressure that those metals achieved. So you can imagine what the pressure steps look like, and this happens very quickly, but you have this time dependence in the pressure until you reach that shock state. Now in a natural event, say an impact, a basin-forming impact on the moon, those materials are going to reach their shock pressure instantly. There's no reverberation of the shock. So there are some differences in the entropy that's created between these two different types of experiments. So while we can say we create the same shock pressure, it's not necessarily the same thermodynamic path between this type of experiment and a real impact. So to get around that, we have to use a different type of gun. And so I'm going to take you over to our second gun. Now, consequently, with this gun, we also get to much higher shock pressures. While we're limited to about 2 kilometers a second with this single stage powder gun, the next gun, which is over here, you can see the target chamber's way over there, that white one. We have this very long gray free flight chamber. Here's the barrel, about 3 feet long, and then it even continues over here to what we call the pump tube. And I'll go describe all that in 1 second. But this is called a 2-stage light gas gun. So we eventually run into a limitation with gunpowder, which is you can only accelerate gunpowder, the gas from gunpowder, so fast when you burn it. And that's getting around 2.5 to 3 kilometers a second. After that, there's diminishing returns. You're not going to get the same amount of velocity. So we have to use a lighter gas, something that can expand even faster. And what the lightest gas is hydrogen. So in this gun, what we're using is gunpowder to accelerate a piston that compresses hydrogen gas to a point where it ruptures the disc and then very quickly expands, much faster than gunpowder can. And then we can reach projectile velocities up to 6.5, maybe even 7 kilometers a second. So before I show you the gun, I'm actually going to show you a quick picture of what this looks like on the inside. So what I'm going to show you is we have our breech assembly on the gun. This is where we put the gunpowder. And then we have a Teflon piston. That gunpowder only propels the piston down the pump tube that is already filled with hydrogen. It's pressurized to about 60 psi with hydrogen. And as that piston advances after the gunpowder fires, this gas becomes condensed, it becomes hot, and it ultimately breaks through this the green diaphragm here, or burst disc, and then accelerates our projectile, which is noted here. And then the key to this type of gun is that happens before the piston reaches the end of the pump tube. So we're still pushing hydrogen through as that projectile is starting to accelerate. So let me show you what that looks like on our gun. So we're down here at the business end. Here's our breech. It's identical to that of the flat plate. So this is where we put in the gunpowder. This is where we would put in the signal and the electric primer to fire the gunpowder. Now in the flat plate, this would be our barrel. But as we said, this is filled with hydrogen, pressurized hydrogen. And we have a Teflon piston that's sitting down here at the end that then starts accelerating and pressurizing this hydrogen, because right here is what we call the high pressure coupling. And this is where we have a burst disc. This is a piece of steel that holds back all that hydrogen pressure until a known, it's calibrated. I should show you one of these. When we reach a known pressure, that disc bursts, and then all of that hydrogen is released from this side. And our projectile, which is sitting right here at the barrel, this is actually the only length of the barrel. It's about 40 inches in comparison to the gun that's about 40 feet long. And then it accelerates from standstill to 6.5 kilometers a second in about 3.5 feet. So let me show you what some of these things look like. So here's one of our Teflon pistons. We machine these in-house. It's a consumable. It has a conical shape at the end. And that is because if you remember from that drawing, which I didn't point out, so that's my fault, but the very end of the pump tube is tapered. And so here's a spent one. This one has been accelerated down to accelerate the hydrogen. And you can see how it has this tapered shape. Well, it didn't start out tapered. And so this eventually stops itself and doesn't embed itself in the barrel. As that hydrogen is getting pressurized, this is our burst disc. So it's just a thin piece of steel with a cross that's machined into it to a precision depth. And that allows it to burst at a known pressure. So this is a spent disc. And you can see when that hydrogen builds up enough pressure, it just breaks through there and then accelerates our projectile. Now our projectile's inside of a sabot. A sabot is a piece of plastic. This is really hard to see at this scale, that we machine out. That O-ring on there is just to hold it together. And it's either 2 pieces or 4, and it allows us to put a projectile, in this case a little black glass sphere, inside of that piece of plastic. And this is what goes down the barrel. It then separates after it leaves the barrel. So the projectile will go down the flight path and ultimately hit our target. In this case, it was just a target practice trying to hit a piece of aluminum. And so just to show you the energy, tiny piece of glass, giant depression in this fairly strong piece of aluminum. Now, as that sabot and that projectile come out, they're compressed against the barrel, and the sabot pieces want to naturally, as soon as they leave the barrel, they want to naturally start separating. So the projectile will go straight down towards the target, and the sabot pieces will start to separate. We have what we call a sabot catcher down at the end, which allows the projectile to go through and the sabot pieces to get caught on this sacrificial plate that allows your projectile to go down and hit your target unencumbered. So we don't have pieces of sabot hitting the target. We know exactly what is going down there and impacting the target. So I think I need to move on for time purposes. But that is our light gas gun. So this allows us to get up to the highest speeds that we can in the impact lab, about 6.5 kilometers a second, and we can do a single shock experiment. So in this, we're not recovering the sample in the same way as we were with the flat plate accelerator. Instead, we are stuck with recovering whatever ejecta or highly shocked material you can get from the inside of your target. Now there's one more gun we have in this lab, and it's another single stage powder gun. So similar to the flat plate, the first one I showed you, but instead it's turned on its head 90 degrees. And the reason we do that is because we're also interested in impacts to understand how impact craters form. And what we need to do is we need to take advantage of the gravitational acceleration of Earth and the gravitational vector. It's hard to put a target on its side because if you notice both of these guns so far, the target is sitting on its side and we impact it from the side. So by turning one of these guns on its head, we can then use buckets of sand and we can impact them from straight down, and we can create impact craters that way and study them. So let me show you a diagram. It's fairly hard to see the whole gun here in the lab without going onto the top floor because this gun actually takes up 2 floors. So this is a schematic of the gun. We have the breech and the barrel and this first chamber all on the 2nd floor in the lab. So the projectile is inside of its sabot, just like the light gas gun. It comes down. We have a flapper valve that helps us eliminate some of the gas that's coming down. It separates the gas from the projectile. A sabot catcher, so you can see the blue projectile here and then the green sabot pieces are being cordoned off to the side. The projectile can go straight through the middle. Similarly to the flat plate, we have some laser velocity stations, and then it enters the impact chamber, which I will go show you now. Exit out there. So it's kind of hard to see. Yeah, I'll just have to walk over there. Sorry, we're kind of learning how to do this together. I'm not an expert at doing virtual lab tours yet. So this is the chamber door for this gun. Can open it up for you. And sorry, I did not put a bucket inside. But inside we have a XY table that we can put our target bucket on. Here we go. Mark Santala to the rescue as usual. Here is our target bucket. It's about 1 foot in diameter and about 5 inches deep. And we can fill that with whatever we want. Loose sand, rocks, a combination of both to simulate different types of planetary surfaces and different material properties. And then our projectile comes through that hole in the back and impacts our target. And we have a few different pieces of analytical equipment installed in here. The first is we have a green laser that skims the very top of the bucket, and we use this to trigger all of the other instruments. So when that green laser is occulted from either the projectile or the ejecta coming off the target, we know that the impact has happened, and then we can start acquiring data. And the main type of data that we acquire in situ is we look at the ejecta. So we're interested in ejecta kinematics. We have something called the ejection velocity measurement system. I want everyone to say that 3 times fast. We'll call it the EVMS for short. And what it uses is a strobed laser and a camera that's located on the outside of the impact chamber, safe. Because when we do these experiments, sand goes everywhere. So any kind of equipment that you want to protect has to go on the outside. So let me show you how this instrument works. I need to set this computer down. This is one of those instruments where a picture is worth 10,000 words. Okay, so here we go. So our impactor is coming down to that gray bucket of sand. It impacts, and then we have this cone of ejecta that's coming off, and it's growing as the crater grows, and this ejecta is moving upwards and outwards. We have a laser sheet that bisects that crater, and it doesn't just turn on. What it does is it strobes at a very fast and known rate while that camera's on the outside of the impact chamber with its shutter open. And so what we end up capturing is a temporal sequence of the ejecta in one picture. So here you can see the impact point is on the bottom right of the image. And then what you're seeing here is the accumulation of all of the ejecta over about 2 seconds. So we are opening the camera shutter, we're flashing that laser. And so if you follow these individual dots, those are individual trajectories from single ejecta particles. So what we do to process this is we go in and we follow them. We say, okay, here's one piece of ejecta, and we digitize all of these points, and then we can fit those to an equation to draw the parabola, and then we know the ejection position, the launch angle, and the speed of all of those individual ejected particles. Now this is a bucket into just cohesionless sand. We start to get some really exciting results when we put in cohesive material. So this right here is a target where I had a cohesive layer inside of it, and we actually had the laser on both sides. And you can see this is a little bit more exciting than just the sand. And then here is a piece of sandstone. You see the extent of the block is about here to here, and then I embedded that in a bucket of sand. And so you see this amazing vertical component of all of this ejecta coming back at very high speeds. And then once that shock wave went through the sandstone and entered the sand, then you start to see very similar ejecta patterns that you did to just the plain sand. So it can give us a lot of very quantitative data on the ejecta kinematics, and we look at that as a function of the target properties. So we can change the density, the porosity, the material, etc. Now here's a pretty cool movie. Hopefully it'll play for you. This is a movie that we made by doing 10 different shots, and we only exposed the camera for 50 milliseconds. Okay, I don't know if that'll work. I guess it will not. I apologize for that. So let me go back to it. It's now behaving. So there's a couple more pieces of analytical equipment that we have at our disposal. This is the real-time profiling system. And similar to the EVMS, it uses a laser sheet, but instead of angled at the ejecta, it's angled down at the impact point. And what this allows us to do is monitor the profile of the crater during its formation. So you can see here at the bottom some snapshots with the time listed in milliseconds in the bottom right-hand corner after an impact. So you can see the very first ejecta coming out. We can start to see the crater walls form in the ejecta curtain. You have some over-steepened walls that then start to modify, collapse, and then you end up with a final crater. So this can be a very powerful tool when looking at crater modification and what's actually going on before the walls start to cover up what's on the bottom of the crater. And then also we have a 3D scanner. This is a very powerful tool for us. So we can conduct these shots, and then we have a rail system that connects to the bottom of the impact chamber, and we can pull our targets out of the chamber very carefully and then scan them with a 3D scanner. And so these are pictures of 8 targets on the left and then 3D scans on the right that I've turned into topographic maps. And that allows us to extract out crater profiles at any location and any azimuth inside of these craters. We preserve it forever, which is fantastic. I'll show you what we used to do before my time. I have some of these experiments right in front of me. I'll show you. And then I mentioned we can do some pretty complex target configurations. This is one where I was putting aggregate on top of loose sand. So I colored the aggregate blue. And if you look very carefully, you'll see this little silver dot. That is the projectile. So it's a 1/8 inch aluminum sphere right in the middle. And I put that there for size reference. And then this is after the impact. And what I wanted to show here is the power of this 3D scanner, because if we look at this crater, which is sort of built to mimic an asteroidal surface, some sort of block-choked rubble pile asteroid, you might say that this is the extent of the crater, what you can see from underneath. But then when we look at the 3D scans of these two targets, you can actually see that there is a higher elevation rim that you can't really see in this picture that we pick up in the 3D scanner. So it's a really fun tool to use, and I'm just starting to explore what this can tell us about these targets and how craters form as a function of the impactor properties and the target properties. So, I probably want to start wrapping up and allowing questions to be answered. I hate giving these things and not allowing any time for questions. I would much prefer to answer questions that you think are important rather than telling you think is important. So if there are any questions, maybe we can move on to that. Oh, sorry. I did forget. I told you I would show you how they saved these targets before. This is resin-coated sand. So they would pour targets, different color sand. They would do an impact experiment, and then you can bake this in an oven and actually recover the target and cut it in half. So I'm sort of getting the same information out of that 3D scanner, except I don't get to see on the inside. And it takes up a lot less space, even though these are really cool to show people when they come in the lab. But with that, I would much rather open it up for discussion and questions. No, unfortunately for us, XY coordinates are in the plane that we're standing, and Z would be our vertical axis. So it would be fantastic if we had that ability. There is a facility that NASA has out in Ames where they have a variable angle gun. So they can shoot vertically like the vertical gun, and they can shoot horizontal like the other two that we have, but they can also change the angle of the entire gun. Unfortunately, we don't have that capability, but would very much love if we had that capability. To look at angles, we do have a clever solution to that, though. If you hang, I have it right here, so if you hang with me while I grab it. So instead of tilting the gun, which would be ideal, we can do something else, and we can tilt the surface of the target. So we can take our standard PVC bucket, and we've made these inserts out of thin aluminum, and then we can pack sand in here and then scrape it off. And so you have a tilted surface before the impact. Now, we do have a limitation there that we can't really pack the material higher than the angle of repose, so about 40 degrees, depending on what you're using. So we have that hard limitation that you wouldn't have for an angled gun, but that's what we're stuck with what we have for now. But very good question. That was fantastic. It's slippery. It allows us to very easily accelerate that down the pump tube without losing energy due to friction. So very close to the right answer, yes. We want to make sure that we transmit as much of that energy from the gunpowder as we can to the projectile through the hydrogen, which is the medium it has to go through to get there. And it also allows us to extract it easily. They get wedged in there fairly tight, and it takes quite some beating with a sledgehammer to actually remove those pistons after the shot. So yes, that is a very good observation as well. These are some fantastic questions. Okay, that's an interesting one. This type of research is unique. There are not many labs that exist that do this type of research. It was not what I went to school for instance, which is encouraging for I think, interns that are interested in it now. As the page mentioned in the introduction, my background was rock physics, so I always dealt with deformation of materials. I was always interested in strain and stress and how materials deform as a function of stress. But I was always working on longer timescales, that of mantle deformation, that of seismic waves, so relatively slow processes. And then after my PhD, I really got the itch to start doing things at faster timescales. And I did a short postdoc at the Institute for Shock Physics in Washington State University. So on the planetary side, there are a few labs that are interested in shock recovery experiments to look at shock calibration of meteorites and minerals. There's a lot more shock experiments that go on the physics side. So in physics departments, they're interested in fundamental properties of materials at extreme conditions, building Hugonio data, equation of state, looking at filling in these thermodynamic parameters that allow you to extrapolate equations of state to, all different types of conditions for materials that we find here on Earth. So there's a lot of opportunities in physics and chemistry for that, and there's a few on the planetary side. I would suggest explore what you find interesting now, because there's always correlations to doing this type of work. For example, we have researchers that come in that are astrobiologists. They want to understand how shock affects organic molecules. People that are interested in, astronomers that are interested in spectra, what happens as a function of impact to spectra from a powdered sample that would represent a planetary surface. So there's a lot of different pathways to get into this type of work. But specific examples would take some more description, I think. But I see Mark just posted his. Mark, do you want to pop on and say something? Okay, he just yelled at me. No, he's too busy typing. I hope that answered your question. That was a very long, roundabout way of saying there's many different ways to get into this type of work, because the background that's needed for it is fairly diverse, which means that you don't need to start studying this from grad school on. Yes, absolutely. Let me grab some of those. So we have, not we, the lab before I arrived has a history of helping out with missions. They were interested in collecting stardust, so we did the, I think it's called the validation tests for stardust. So it'd be probably really hard to see. This is a chunk of aerogel, and I don't know if you'll be able to see the tracks in it. Oh yeah, you can. See those tracks? Those are impacts from dust-sized particles in our gun, to make sure that this sort of technology worked to capture these very fast particles in a very low density medium. There was also some work on LDEF, which there's a picture right behind me. This was a satellite that orbited, I believe, for 69 months in low Earth orbit and had all different types of materials all over it. And they were interested to send this up there, let it orbit for a while, bring it back down, and try and learn something about the impacts that occurred on the surface to teach us something about shielding for future flight hardware. The simulants, yes. The actual soils, the lunar soils, I could not speak to that. That would have been before my time. I believe I have some samples upstairs that were given to me by Fred Hertz that were shocked lunar samples, but I couldn't tell you to the extent of that. But of course, any kind of simulant we can put in here, especially in the flat plate, we have the ability to pack in a powder and shock it. And there are a few proposals out right now to use this lab that are looking at that exact thing. We use a very high-tech method. We use compressed air to gather it all together, and then we just sweep it with a little handheld broom. But the fun thing about that is that this stuff will get everywhere and it'll hide in places. So I'll do a shot and some chunk of rock will fall out, and I'll go, Mark, what is this? And he goes, oh, that's from a granodiorite that we shot 20 years ago. Because this stuff just gets pulverized and thrown everywhere, and it just hides in the back of the gun. And for example, I did some shots into plastic sand about a year and a half ago, and we've done about 50 shots since. And then I cleaned out the chamber yesterday, and I had about a tablespoon of plastic sand that came out. So you can never really clean it. I don't think you could ever get that thing perfectly clean at this point because that sand just hides everywhere. It is sand-sized pieces of plastic. So I was interested in looking at the effective density on the morphometry of impact craters. And so I was using sand that had a variety of different densities to it. So I bought stainless steel sand, so tiny sand-sized particles that are steel. And I went all the way down to some of the lightest material that I could find, which was plastic. That's a tricky one. So there are different ways that we can make these targets, not just with sand, to sort of get at that. Now, we would probably never be able to completely replicate the surface of like a fairy castle structure, if that's what you're getting at. But people have come up with some really creative things to do in that aspect, mixing multiple materials together, using materials that have incredibly high intragranular porosity. So like pumice, for instance, you can have a chunk of pumice that is 95% air, but there are still, even if you were to replicate that material identically, there's still a lot of parameters that we can't replicate, such as the gravity situation. We're sort of stuck with 1G unless we do these experiments on aircraft, which they have done in the past. I don't know if the picture's here or if it's been put away. Oh, it's been put away. But back in the 80s and 90s, Mark and a few of the gunners here were doing experiments on the KC-135 at low G and 0G. So they had an impact chamber in a plane that would do parabolic flights, and they were coming down and able to do these experiments at simulated lunar gravity or asteroidal gravity. That's an interesting question. So it's sort of, if a tree falls in the forest, does it make a sound? So inside of the chamber itself is under vacuum. So we do all of these experiments under vacuum for a couple reasons. First, we want to eliminate as much drag as possible on the projectile because, again, we're trying to get as much energy downrange into the target that we can. But that also means that no sound can be propagated. So if these two pieces of metal smack together in vacuum, they don't make any sound. But what they do is, since they're connected to the gun and the gun is connected to the concrete through very sturdy bolts, it creates a rumble. So we're basically turning the gun into a drum, and then that's vibrating the air on the outside of it, and you can hear that. But the actual impact, no. When you're outside and we're shooting, what I like to tell visitors is to put their back up against the wall, because you can feel it on the wall a lot more than what you can hear. And it's pretty amazing, especially when we do these higher pressure shots on the flat plate. When you have this chunk of metal flying around at 2 kilometers a second, it makes quite a percussive vibration in the walls and in the ground. So it's pretty neat. But for the vertical gun, we're so far away from it, and you have this big momentum trap of the sand target. I don't want to say that it's anticlimactic, but people come here thinking that you're going to hear this giant boom, but you really don't. We have to actually really listen for it to make sure that it fired. And the way that we really know it did is we have a pressure gauge or a vacuum gauge. And if we see a jump up in pressure, we know that the gun fired because the gas that was expelled from the gunpowder breaks our vacuum slightly. So you can actually see that more than you can hear the gun. So it's a little bit of both, but no microphones, no. Yeah, absolutely. I think that's a very important question because it's something that no one told me when I was going through school. And I was always under the impression that I would be stuck doing what I was doing in grad school for the rest of my life. So I studied olivine for about 10 years and its mechanical properties, and I knew it like the back of my hand. And it got to the point where I didn't really want to do that anymore. But during the course of my graduate studies, I tried to branch out as much as I possibly could to learn not just not other disciplines, but other skills. So working on as much equipment as I could, learning as much equipment as I could, because what's really amazing is that you don't realize at the time how that experience will come back and benefit you. So, for instance, one of the pieces of equipment I worked on for my PhD was a high pressure gas apparatus. So we would use gas to pressurize a sample instead of solid medium. And so I learned a lot about hydraulics. I learned a lot about vacuum systems. And lo and behold, I mean, you look around, this whole thing is a big vacuum system. We're at high gas pressures. And so you learn these skills that you don't realize that you're learning, that they can benefit you in other fields, but you don't really see that connection right away. So I would definitely say pursue what you find interesting, dip your hand in as much as you possibly can to gain as much experience as you can, and it'll all come together, and you won't realize how it'll come together until it actually does. I know we're out of time. I just wanted to say if any of the interns had specific questions, please feel free to email me. I'm always available, and I'm not too far out of where you are in your academic journey. I'm about 4 years post PhD, so this is it's timely. So please, if you have any other questions, just reach out. And thank you very much for your attention. I appreciate it.